Okay, hi. Our topic today is unsupervised learning. So, I think we have covered quite a lot in this class on supervised learning methods, yeah, such as regressions and classifications. So, when we talk about supervised learning methods, so we deal with models where we use a set of independent variables to explain about the variations of the dependent variables. So we are using a set of features to explain about the target variable. Yeah, and the target variable can be both numerical and can be categorical. So in the past few weeks, we have learned how to do linear regression, and then the logistic regressions, the tree-based methods, which includes the regression tree and also the classification tree. So today our method is going to be totally different from what we have covered so far, in which we're going to learn about unsupervised learning. And the starking difference between unsupervised learning and the supervised learning is the absence of the target variable. So we only have a set of features or a set of independent variables. Okay. So basically, the goal of unsupervised learning is to discover interesting things about the measurements on the X variables. So it's quite different from the supervised learning methods, in which in supervised learning methods we are interested in doing the prediction. So of course, when we talk about prediction, we want to find the model which can increase the prediction accuracy. Okay, so we look at the data, we look at the relationship between the variables, and then if the relationship is quite linear, then we are satisfied with using the linear regressions. If it can minimize the sum of squared error, and it also can increase the prediction accuracy, then we are happy with that. But when we talk about unsupervised learning, it doesn't involve any predictions. So we are going to use several models to discover any patterns, any underlying patterns in our data sets. Okay, so there are several questions that we can ask when we do this supervised learning. Is there an informative way to visualize the data? Or can we discover subgroups among the variables or among the observations? Okay, so there are many unsupervised learning models out there, but we are going to cover a few. And the first one is we are going to talk about the principal component analysis, or the PCA. So PCA can be used as a dimensional reduction methods. It can also use for data visualizations or data pre-processing before supervised learning techniques are applied. So what it means here is that if you are happen to be dealing with a lot of X variables, and then you want to reduce the number of the X variables, and then you can use PCA, and then based on the results from the PCA, then you can feed into any of the supervised learning techniques. And then another part is we are going to cover the clustering methods, and these clustering methods have a broad class of methods for discovering unknown subgroups in data. So basically we're going to cover two. Number one is the hierarchical clustering. The other one is the k-means clustering. Okay, so when we talk about unsupervised learning methods, it tends to be more subjective, and there's no simple goal for the analysis. Like in the prediction, when we deal with supervised learnings, when we do predictions, so there's like a specific statistical analysis or statistical evaluations that we can use. Like for example, the misclassification rate, in order for us to evaluate whether this model have a high misclassification error rate, or it has a high prediction accuracy. So you can compare from one model to another, and you can see the performance of the models. Yeah, but when we talk about unsupervised learning, there's really no way of telling whether this model is going to be better than that model, because we are not predicting anything. We're just discovering patterns, and then we just look at those patterns. Yeah. The unsupervised learning is also often performed as part of an exploratory data analysis. So first is before you do any supervised learning methods, you do this any methods under the unsupervised learning to understand better about the patterns in your data. And then it is also hard to assess the results obtained from the unsupervised learning methods, because this is related to point number 1, because the unsupervised learning methods, the results are quite subjective in terms of evaluation. Okay, let's talk about a few examples in which the unsupervised learning methods are being employed. In the first example, we have a cancer researcher might assay gene expressions levels in 100 patients with breast cancer. So he or she might then look for subgroups among the breast cancer samples or among the genes in order to obtain a better understanding of the disease. So this is one example in which we do not have any target variable. We're just looking at the genes, or we are looking at the cancer samples, and we want to look is there's any proteins, you know, that are more related to another, is there's any subtype of breast cancer. And in another example, we have in marketing, we have an online shopping site who might try to identify groups of shoppers with similar browsing and purchase histories, as well as items that are of particular interest to the shoppers within each group. Then an individual shopper can be preferentially shown the items in which he or she is particularly likely to be interested based on the purchase histories of similar shoppers. So in this case, we can group the shoppers into based on the demographic profile, where we might have like a young females aged 19 to 22, and they have like a very different preferential of items that they're going to buy compared to males aged 50 and above, you know, who are more likely be interested in buying things like camping and camping tent and fishing nets and all that. Okay. All right. Another example is a search engine. So this is also more related to the second example. So a search engine might choose what search results to display to a particular individual based on the click histories or other individuals with similar search patterns. Like for example, if you use Google, okay, and then you search, your search history is going to be uniquely different from someone else, you know. And then maybe you're a student and you spend more time in using Google Scholars, and then you look for papers, you look for academic articles and all that, compared to like school children. Their search history might be different from yours. So the search engine might choose what kind of results they are going to show. This is also true when you use like social media and you see a lot of advertisement, you know. So they actually look at your history of clicks, and then they look at your interests, and then they try to sell you something that is that makes you more likely to buy. Okay, now let us talk about the first one, which is the principal component analysis. So the PCA, as I mentioned, it is used as a data dimensional reduction technique. Yeah. So when you have like a large set of correlated variables, so some variables are correlated to another, like you have x1, x2, x3 and x4 are correlated, and then you have x5, x6 and x7 are more correlated, you know. So you can use the principal components to summarize this set with a smaller number of representative variables that collectively explain most of the variability in the original set. So PCA is considered an unsupervised approach since it involves only a set of features, which is the x variables, and there's no associated response y variables. So you just look at the x variables, and that is why the results from the PCA later on you can use this reduce x variables in the supervised learning. So let's look at this one. Let's say we have a data set. We have about 50 observations, and we use a scatter plot to show the relationship between populations and the advertisement spending. So you can see the higher the population, the higher the advertisement spending is. And we try to just you know, usually when we only have like two variables, we don't need the PCA, right? Because we only have like two variables. But just take this as an example to make it easy for us to understand the concepts of PCA. So you can see clearly there is a positive relationship between the two variables. And then when you conduct the PCA, it comes out with several principal components. Yeah. So the first component that you can see here is the directions of the data, that is along which the observations vary the most. So it is represented by the green solid line that you can see here. So this is the first principle. It covers most variations that exist in the data sets. Yeah. So the green solid line represents the first principal component directions of the data. And if we try to project the 100 observations onto this line, then the resulting projected observations would have the largest possible variance, and projecting the observations onto any other line would yield projected observations with lower variance. So in this case, once you have this, the first principal component, which is represented by the green line on the left graph, and then you try to map this first principal component with the second principal components, you can see that most of the variations actually being captured by the first principal components. And the first principal components is represented by Z1, okay, and this is given by phi value. Phi is the loadings for population, which is 0.839, and then you have the loadings for the advertisement, which is 0.544. So both of these values, the loadings for population and the loadings for advertisement, actually explain, or it defines, the direction. So now let's look at the second principle. Yeah. So the second principle is represented by the dash line, the dash blue line over here, because first you have captured most of the variability in the data sets, which is the green line, and you have already captured that. So the second kind of variation occurs diagonal to the first line, which is represented by this dash blue line. Okay, and the loadings for population is given by 0.5, and the loadings for the advertisement is given by negative 0.83. So since this data sets only have like two predictors, so the first two principal components contain all of the information there is in population and advertisement. So by constructions, there will always be like the first component will always contain the most information, and then the second component will contain the, you know, less variation, and the third one, and so on and so forth. Okay, so since these data sets only have like two predictors, so we can only come up with two components. Okay, however, as you look at this compared to the first component, okay, in which you can see that it managed to capture most variation, but in the second component, when you try to map the second principal component with the advertisement spending as well as the population, you can see that there is very little relationship between the second principal components and the two predictors. Yeah. So the fact that the second principal component scores are much closer to zero indicates that this component captures far less information compared to the first component. And later on in the lab sessions, we are going to look at how much variation is being held by each of these components, and then we're going to decide, like for example, we're going to deal with a larger data sets would have more features, and then we are going to decide at what point are we going to stop, you know, the number of the components. Okay, now let's use an example of the US arrest data sets, and this data set is available in R. So for each of the 50 states in the United States, the data set contains the number of arrests per 100,000 residents for each of the three crimes. We have assault, murder, and rape. So we also have the fourth variable, which is the urban population, which is the percentage of the population in each state living in an urban areas. And then we're going to look at these data sets, and then we're going to use the PCA, and we want to see whether it is possible for us to reduce the dimensions, because here we have like 4 variables. Is it possible for us to reduce the the number of features in these data sets? So the principal components core vectors, in this case, we have a length of n equal to 50 observations, and the principal components loading vectors will have a length of p equal to 4 features. So PCA was performed after standardizing each variable to have a mean of 0 and the standard deviations of 1. And this is very important, yeah? So I'm going to discuss about this later on, why we need to standardize the variable to have a mean of 0 and standard deviations of 1. Now, the first principal components of a set of features x1, x2, xp is the normalized linear combinations of the features z1. Okay, so the phi 11 is the loadings for the first variable, phi 21 is the loading of the second variable, and so on. So the first component will have the largest variance, and then we normalize by getting the sum of all the phi squared must be equal to 1. So once we have computed the principal components, we can plot them against each other in order to produce a low dimensional views of the data. Now let's look at this example using the US arrest data sets. So each of this name is the name of the states. Yeah, there are 50 states in this graph, and then we plot the first 2 principal components. So you can see the first principal components is on the horizontal axis, and the second principal components is on the vertical axis. So the first loading vectors place approximately equal weight on the assault, murder, and rape. As you can see, they are close together, and then the second loading vector places most of its weight on the urban population. So now let's look at the first principal components here. So the locations of the murder, assaults, and rapes, not only they are close to each other, but they are positive, which means that they have a positive value for the first principal components. And we can also say that these 3 are more related compared to the urban population. But in case of the urban population, it is very, very far away from the other 3, and it has a high value in the second principal components. So we can see that the crime related variables such as the murder, assaults, and rape are located close to each other, and that the urban population variable is far from the other 3. So what does it mean? It may indicate that the crime related variables are correlated with each other. So if these states have a high murder rates, it also tend to have a high assault and high rape rates, and that the urban population variable is less correlated with the other 3. Now if we look at this specific states, yeah, like this one, Georgia, Alaska, and Alabama, they have a low rate on the urban population, which means that they are less urban, but they have a very, very high murder, the rate of murder. Okay, and Maryland is very close to assaults, and New York, Colorado, they have a little bit high. They are a bit high on the urban population, but they also have like a high rate for rape. Yeah. So if you look at the locations of the states, we can say that the states with large positive scores on the first component, such as California, Nevada, Florida, have high crime rates, while states such as North Dakota with negative scores on the first component have low crime rates. Now let's look at this. Yeah, so this is, where is North Dakota? It's somewhere here. Okay, it is also okay, let me see first. Okay, California, Nevada, and Nevada is here, California is here, and Florida is here. They're very, very high in terms of in terms of the crime rates, and North Dakota is very, very low in terms of the crime rate. And in terms of the urban population, we can see that the New Jersey, California are on the high score, but Mississippi and Kentucky, for example, they have a lower score. Alabama have a lower score on the urban population. So let's just look at this here. California also has a high score on the second component, indicating a high level of urbanization, while the opposite is true for states like Mississippi, which is low in urbanization. And states close to zero on both components, such as Indiana, have approximately average level of both crime and urbanization. Now let's look at this. So I believe that Indiana and Virginia, Missouri, for example, Missouri might be a little bit higher score in crime rates compared to Indiana, but Indiana and Virginia, they have like an average of urbanization and also average in terms of crimes. Okay, so the principal component loadings for each of these three crimes and also for the urban populations is given by this. So we can see that murder is somewhere murder is centered somewhere of murder is centered at 0.53, which is, if you look at murder here, so 0.53 on the x-axis is somewhere there. Okay, and then it also corresponds to the loadings of second component, which is negative 0.4. Okay, and assault is centered around 0.58 and negative 0.18 for the second component, and so with the rest. Yeah. Okay, so now let's go back to the point I mentioned earlier, why there is a need to scale the variables, where we need to set the mean equal to 0 and the standard deviation is equal to 1. So before the principal components analysis is performed, the variable should be centered to have a mean of 0. So the results obtained depends on whether the variable have been individually scaled, okay, in which each multiplied by a different constant. So why does it matter? Why is it important? So the variables are measured in different units. In this case, okay, when we use the US arrest data, you can run the summary function in R to look at this. So the murder, rape and assault are reported as the number of occurrences per 100,000 people, and the urban population is the percentage of the state's population that lives in an urban area. If you just look at the variance of these four variables, you can see that the variance for murder is 18 and rape is 87, and the assault is much higher, so it's close to 7,000, and the urban pop is 209. So if we perform the principal component analysis on the unscaled variables, then the first principal component loading vector will have a very large loading for assault, because the variation in assault is so much higher than the rest of the variables. So now let's look at this one. On the left hand side you have a similar output that we have discussed before, but on the right hand side you have the one with the unscaled variable. So the first principal component biplots for the US arrest data. Okay, assault, as you can see on the right hand side, has by far the largest loading on the first principal components, because it has the highest variance among the four variables. Okay, so you can see that looking at this, it looks like it is far away from the other two crimes. So that is why it is suggested that you scale the variables to have a standard deviations of 1. Okay, now we would like to look at the proportions of variance being explained by each of the components. So how much of the information is lost by projecting the observations onto the first few principal components? So imagine if you deal with large data sets, with lots of P features, and then you just reduce the dimensions into 4 to 5 components. So you want to know how much of the information is actually lost. Okay, so basically we're interested in knowing the proportions of variance explained, or the PVE, by each of the principal component. So look at this one. The left one is the script plot, which depict the proportions of variance explained by each of the 4 principal components in the case of US arrest data. So we just consider 4 because we only have like 4 features. Yeah. And then on the right hand side is the same plot, but this one is a cumulative proportions of variance. So you can see on the left one, yeah. So the first one is the first principal component, and it explains 62% of the variations in the data. So it's like just a little bit above 0.6 here. And then you can see that the first principle will always have the largest variance, and it will always go down. Okay. So the second principle explain 24.7% of the variance. So together they explain about, so this is the first one. When you go to the second one, this is like 80 something, okay, 87% of the variations in the data can be explained by the first and the second principle. So if you look at the third principal component, you see that the value is maybe 0.13, yeah, and then it only adds a little bit when you look at the plot on the right hand side. Okay, so that was the principal components analysis. Now we would like to discuss about clustering methods. Okay, so when we talk about clustering methods, we refer to a very broad set of techniques for finding subgroups or clusters in the data sets. So the goal of the clustering methods is to partition them, or partition this data into distinct groups so that the observations within each group are quite similar to each other, okay, but they are different from individuals from another groups. So let's take the marketing example again here. So you have like a pool of customers, and then you want to see whether a subgroup exists in your customers, especially in terms of preferential of purchasing things, yeah, because you want to increase sales, so you want to suggest or you want to give recommendations to different groups of people on buying different things. Okay, so first, when we do these clustering methods, this is very important. We must define what it means for 2 or more observations to be similar or different. How do we want to define it? So in this case, we need a domain-specific considerations. So when you deal with the gene expressions, at least you understand what you are trying to look at, what you are trying to see. Okay, and then when you are working with a marketing, for marketing example, so you need to know what are you really looking for. Okay, so let's take an example of this where we are looking for a subtype of breast cancer. So let's say we have n observations and p features, where the observations are the tissue samples for patients with breast cancer, and then in terms of the features, we have the measurements collected for each tissue samples. So we can have like a large features, so you can have a tumor stage, you can have information on the tumor stage, or you can have information on the grade or the gene expressions. Okay, so there might be some heterogeneity among the n tissue samples. Perhaps there are a few different unknown subtypes of breast cancer, and you are interested in looking at how the tissues or how the biomarkers or the gene expressions are more similar to each other or is different from each other. So the clustering technique could be used to find these subgroups. Okay, so now we are wondering what is the difference between the PCA and the clustering techniques that we are going to cover later. So PCA looks to find a low dimensional representations of the observations that explains a good fractions of the variance, while the clustering looks to find homogeneous subgroups among the observations. Okay, so PCA basically it reduces the dimensions of the data so long as it still maintain the variability, but the clustering, they're looking for the subgroups in the data that are more similar to each other. Okay. And now uh, the second clustering methods that we are going to learn is the k-means clustering. So k-means clustering is a simple and elegant approach for partitioning a data into k distinct, non-overlapping clusters. And I would say k-means is one of the easiest clustering methods that you can do. Maybe you can use this as a baseline. So to perform the k-means clustering, we must first specify the desired numbers of clusters k. Okay, so how many clusters do you want to have in this data sets? You're going to have like 2 clusters, 3 clusters, or 4 clusters, and etc. Then the k-means algorithm will assign each observations to exactly one of the k clusters. Now let's look at this example. So we have this data which look exactly the same. This is the relationship between the data between x and x1 and x2, for example. And then when you use k equal to 2, so you come up with 2 clusters. In the middle graph it shows 3 clusters, and then in the third graph it shows 4 clusters. And the different colors shows the data which belongs to one specific clusters. So this is the algorithm of the k-means clustering. Okay, so the first step is it randomly assign a number from 1 to k to each of the observations, and this serves as the initial cluster assignment for the observations. And then it will iterate until the cluster assignments stop changing. Okay, so in this iteration, for each of the k clusters, it will compute the cluster centroid on the middle locations of the cluster. And the kth cluster centroid is the vector of the p feature means for the observation in the kth clusters. And then it will assign each observation to the cluster whose centroid is closest. Okay, and when we mean closest, it is defined by using the Euclidean distance. Euclidean distance is a straight line between one point to another. Now let's look at how this algorithm works. So you look at the first graph, and these are all this is the distributions of the data, and in this case, like, we may have like x1 and x2 in this case. So the first step is we just randomly assign. Okay, you just randomly assign, like observation number 1 you just assign to cluster number 1, observation number 2 to cluster number 3, and so on. So you just make it random. So you can see 3 colors here. Okay, you have yellow, pink, and green. And then what you do in the third graph is, based on all this, you just focus on yellow, and then you find where is the centroid of this yellow cluster. Okay, where is the middle point of this yellow cluster, and you put the middle point there. And then you do the same for the green and for the pink one. Okay, so this one we have 3 because we have already decided that we are going to have 3 clusters. So you can see that they are overlapping with each other. Never mind. And then you iterate again. So that's why this algorithm, it will iterate until there will be no more changes. So in the fourth graph, you reassign each of the observations based on the closest cluster centroid. Okay, so if this one, look at the third graph, if this one, this group is actually closest to the yellow centroid, it will change the color from any other color to yellow. So whoever is closest to each of this centroid will change the color according to the centroid. Okay, and then what you do in the next step, in the fifth graph, is that you relocate the middle point, or you relocate the centroid. So you can see that the centroid for yellow has moved to the middle of the yellow cluster here, and then the pink one has moved to the middle of the pink clusters, and so on. And then what you do is you reassign again. So let me see. Okay, this particular dot is yellow, but when you reassign all the observation based on the closest centroid, you can see that this point has turned pink. And this too was yellow in the fifth graph, and it turns green in the last graph because you reassign. And then what you do is that once you reassign the observation, you do it again and again and again. You iterate until there will be no more changes. Okay, So now we would like to talk about hierarchical clustering. So the difference between hierarchical clustering and the k-means clustering is, number one, you do not have to specify the number of clusters, and sometimes I think this is also important because sometimes you will never know how many clusters you should have in your data set. And number two, it has an added advantage because it results in an attractive tree-based representations of the observation. So just like regression tree, we might want to use regression tree instead of any other models because it's easier to interpret because you can see clearly. So the resulting output from the clustering technique, from the hierarchical clustering technique, can be seen in terms of dendrogram. Okay. So the dendrogram is you have the cutoff value on the vertical on the vertical axis here. So depends on your cutoff value, your number of clusters depends on your cutoff value. Like for example, on the left hand side you do not have any cutoff value, so all of the observation belong to one group. Okay, but if you cut off at around 9 here, so you can see the dash line here, you have like it intercepts with 2 lines here, so that means that you have 2 groups. So the first group is whatever it is under this branch, and we color it as red, and then the other one is green, which is whichever observation falls under this branch. And if you cut off around 5 here, you have like 1 and 2 and 3 groups, and then the color corresponds to the 3 groups that has been selected. As you lower the cutoff value, you're going to have more and more, and then finally you have an individual observation. So what is the algorithm for hierarchical clustering? So first we begin with n observations and a measure, such as Euclidean distance of all the pairwise dissimilarity. So first is we compute the dissimilarity between one observations to another, and we treat each observation as its own cluster. So we start with the number of observation first, and then we do this iteration in the second steps. So in the iterations, we examine all the pairwise intercluster dissimilarity among the I cluster, and then we identify the pair of clusters that are least dissimilar, okay, or they are close to each other, they are mostly similar to each other, and then we fuse these 2 clusters. Okay, when I say clusters, in the first step it is observation before it becomes clusters. So the dissimilarity between these 2 clusters indicates the height in the dendrogram at which the fusion should be placed. So if they are closer together in terms of the heights of the dendrogram, it means that they are similar. If they are further away, it means that they are dissimilar. And then we compute the new pairwise intercluster dissimilarities among the I-1 remaining clusters, and then we do it again and again and again until there was only one group. Okay, so on top of this dendrogram there's only one group, but as you go down below you can have like 2 groups, and then you have 3 groups, and so on and so forth. Okay, so let me just try to explain using this. So look at this number, and the first graph shows the raw observations. Okay, and then in the second graph we may want to start with first is each of these observation become its own cluster, and we compute the dissimilarity between any 2 pairwise, between, like for example, between 7 and 5, between 7 and 8, maybe between 1 and 6, and so on. So we choose the one that is most similar to each other, which is 7 and 5 are closer to each other. So 7 and 5 becomes one cluster, and then we look at all the other clusters. We do the same, yeah, we do for these clusters and number 9, this cluster and number 8, and we also do the individual observation as well. And then we find that the second cluster is 1 and 6, and then we do it again, and then we find that this cluster of 7 and 5 are more similar to number 8, and then we group them together. So what we have is, okay, yeah, I really hope I have that information here. Yeah, but it should appear as clusters like this, where 7 and 5 are closer to each other, and then you have 8, but 1 and 6 are maybe somewhere around here. Okay, So we will continue with the lab session. And for the lab session, first we are going to use the US arrest data, and we are going to conduct the PCA analysis based on these data sets. So first I'm just going to call the data US arrest, and then I just want to run some SDR functions on these data sets. And I see that these data sets will have 50 observations based on 4 variables. And let me just see if everything is okay. And let's just run some summary of this here. Summary of US arrest, and you can see the minimum, the maximum, and the median, the mean value of all the 4 variables. And from the lecture notes that we have discussed earlier, we can see that assault is having the largest variation. So you can see from the minimum value to the maximum value, the variation is very, very high. Yeah. So we just do the PCA based on this without scaling the variables first. So we are going to end up having a bias output. Okay. So let's just run some okay, so first is I'm going to create a vector named states, and states is the row names of the US arrests, and I'm going to show all the 50 states. And then this is all the names of the columns in US arrests. And then we're going to use the apply functions. The apply function is actually, we want to compute the mean for each of the 4 variables. So we don't have to type in mean of murder, mean of assault one by one. So what you can do is we can use just apply, then apply on all the columns in US arrests. And then we just want to find out the mean. Okay. I can't really remember 2 means what, yeah, in this case. So I'm just going to use this help function to find out what does this 2 means. So this is a function apply on US arrest. 2 means the second dimension, is it? Okay, so in this case I really can't remember what this 2 means. Yeah, so let's just KIV that for a moment, and then we do the same for the variance. So we just apply of US arrest 2, and then the variance, and this is the variance for each of the 4 variables. So you can see the mean is also different, like murder has a very low mean compared to the rest. And also in terms of the variations, we can see that assault is having the largest variation. Okay, so right, and now we want to perform the principal component analysis using the prcomp function. So we just save all the output in pr.out, and then we just run the prcomp using the US arrest data. Scale is set to be true, so automatically you don't have to do it yourself, but using the prcomp you can automatically scale each of the variables. Okay, and then let's see what is there in the in this pr.out. So you just type it there. So there are several objects that you have in pr.out, mainly the sdef, the rotation, the center, scale, and X. So we are interested in looking at the component loading is given by this rotation. So you can see that the loadings for murder in the first principle is given by negative 0.53, and then in the second component it is 0.4. So you look at this number, it seems like this is quite familiar, yeah, except that in the lecture notes they are in the inverse sign. So let me just go back to the US arrest data. It's somewhere here, I think. This one. So you can see that murder, the loadings for murder from the first principle is positive 0.53, and in the second loading it is negative 0.41. Okay, so why there is a difference? Let us just look at this. Okay, let me just find out. Okay, so the sign here is just the difference in terms of the sign is just the way that this textbook actually want to show the graph. Okay, so it really doesn't matter, because if later on I'm going to show you that we are going to develop the graph, and then it's going to show the locations of the directions of each of these principal component here. So let me just show the biplot first. Okay, I'm going to zoom in. So this is how the biplot looks like. It is a mirror of the biplot that we have in our lecture notes. So but it explains the same thing, because here what you have here is you have the first component over here, and then this is the second component. Okay, it tells the same story, where the murder, assault and rape, the three crimes, are much closer to each other compared to the urban pop, except the direction is different. Okay, so let me just look at this one to get the graph exactly like in the lecture notes. So we just change the the sign from positive to negative. So that is what I'm going to do now. So first is I change the rotations to be negative of rotation, and then these the value of x is also the inverse sign of value of x, and then we do the same biplot, and you can see that this is exactly the biplot that we had in the lecture notes. Okay, so now we want to look at the proportions of variance explained by each of the principal components. So for this one, we're going to use the SDEF, this one, the SDEF from the PR.out. So SDEF is actually the standard deviation. So to get the variance, so we just square the standard deviation, and then to compute the PVE, so this is equal to the variations divided by the sum of all the variation. So that is what we are going to do. So first is PR.var is given by PR.out $ standard deviation squared, so we get the variance, and then we compute the PVE, which is each of the variance divided by the sum of all the variance, and then this is the PVE value. So you can see that the first component, the variance that is being explained by the first component is 62%, and in the second component is 24%, and it reduced to 0.08% in the third component, and then finally the fourth component. Okay, now we want to create the script plot for this PVE. So first is we show the PVE, and then we show the cumulative PVE. So you can see the first one is that we plot the PVE itself, and the second one is we use the function CumSum, which is the cumulative sum of the PVE. And this is the script plot. It explains the same thing. So this is the first variance explained by the first component, and this is the second component, third component, and fourth component, and on the right hand side is the cumulative. Okay, so for the k-means clustering, we are going to create a simulated data with two clusters. So first is I'm going to clean this console, and okay, so first is I'm going to use the set.seed. So basically, because we're going to use some random sample, which is let me just clean this one. Okay, so let me just type in rnorm of 10 numbers. So I get this one, and I run it again, and I get different numbers and different numbers every time. But in order for me to have a reproducible results, and in order for me and you to have exactly the same results, so we are going to use the set.seeds. So it fixed the randomness in the samples. So let's say I'm going to use set. You can put any numbers here, yeah. So I'm just using this number, and then now I want to come up with R norm of 10. So that is, and then if I want to repeat again, so I can just type in. So you can see that the last two are exactly the same. Okay, but don't be scared if you don't get exactly the same number as mine, because for some reason this is pseudo numbers, yeah. And I find that in many cases there will be 1 or 2 students in my class who don't get exactly the same answer as mine, because it's probably because of some initial state of your random number generation based on your own computer. Okay, I can't explain that, but the thing is not exactly the number that we have here. The thing is that the approach that you know that you do in the class. Okay, so now we're going to use set of 2, and then we're going to create a random number here. We're going to create a random number of 50 times 2, which is 100 numbers, okay, with 2 columns, but we're going to save this into a matrix. So you can type in the dimensions of the matrix here, dim of x. We have like 50 rows and 2 columns. Okay, so first is I'm going to create x from observation 1 to 25. Okay, from the first column I'm going to copy the same number plus 3, and then in from the first 25 observations from the second column, I'm going to copy the same number minus 4. Okay, so this is just to create clusters, or this is just to create a mean shift of the first 25 numbers compared to the next 25 numbers. Because we want to create the 2 clusters, so we have to tweak the data a little bit. Okay, so now we want to let it just play along. Okay, play around this one. So let's say I want to plot x first column and then x second column. So the data should look like that. Alright. Okay, so this is how the data looks like. Because what we do is we try to shift the data a little bit. The first 25 observations of the first and the second column, we shift it a little bit, so we have like 2 clusters like this. So this is what we do, yeah. Okay, so now we want to perform the k-means clustering, and because we are the one who generate the data set, so we know that we have like 2 groups. So here we use the k-means functions. K-means of the data set x, where the number of clusters is equal to 2, and n start we set it to be 20. Okay, so we save this as km.out, and then now we want to show all the clusters. So we can see that the first observation belongs to the first clusters, and then the second half of the observation belongs to the second clusters. And then we want to plot this. Okay, so we want to plot this cluster. So what we do is the color is equal to the clusters, and then main is just the labels. Okay, and then PCH is the shape of the dot, and CEX is actually the size of the dots. You can try to tweak in the number here, and then you can see that the graph changes a little bit in terms of the presentation. Okay, alright, so this is the k-means clustering, and it is advisable if you have like a larger data sets, and then maybe you can explore the k-means analysis, running the k-means analysis on the larger data sets here. So this one we have a very small data set. Now we would like to move on to the hierarchical clustering. So for the hierarchical clustering, we will also be using the same data sets x, and then the first one is because we are going to use different methods here. The first one is the complete, and then average and single, and then now we just use the hclass function to come up with the clustering output. And then now we want to plot all the clustering dendrograms. So we are using different linkages here. The first one is the complete linkages, and then we have the average linkage and the single linkage. Okay, so this is how it is. So let's look at the complete linkage, for example. So this is the height of the dendrogram. So at the height of 6, for example, if you cut through at 6, you know that you have like 2 clusters. As you go down, you can have more clusters, and towards the bottom you're going to end up having all of the observation as their own clusters. Okay, so it's quite hard to see unless you really zoom in, but I can see that observation number 12 and observation number 2 are more related to each other, you know. And then if you cut off any of the branch here, you can see that which observations are more similar to each other. Okay, and then finally we're going to determine the cluster labels. So based on the complete linkage, this is how the clustering looks like. Not so much different, but except for the singles. Yeah, in the singles we actually, from the hierarchical clustering, we group most of the observations in the first clusters. Only in the this observation belongs to the second clusters, which you can see here. So this is something that is quite weird. Yeah, so based on the single linkage, it assumes that 16 is very different from the rest of the numbers. And then here 42 is also seems like more distant to the rest of these numbers. Yeah, and then the rest of them we can look at where you cut off the point. Okay, so I think that's all the lab sessions for the unsupervised learning methods. Okay, thank you.